Good morning, folks. This is Todd Coburn of Cal Poly Pomona with lecture 14 of Aero 3261. Today we're going to be extending our look into the slope and deflection calculations for beams, and we're going to be looking specifically at indeterminate beams. Let's see how this works. Now, before we get started, let's recall what we've already learned. We've already seen the elastic curve shown here on the upper left. We saw the elastic curve was that imaginary curve at the neutral axis of a beam that moves, that is located at the centroid of that beam. So we can see it actually represents the shape. So we talk about the equation of the elastic curve. We can talk about, often what we're talking about is the deflection location. So we're talking that y dimension, plus or minus deflection. If this was the initial position, we see all along here, we can define the position of the curve as just a deflection number. We can see the same thing for this other beam, where we see that elastic curve runs along the midplane of that element. We also saw that the change in shear with respect to x was the loading. So if we have a loading, then the shear changes. If there's a transverse force, whether it's a distributed force or a point force, then the internal shear changes. If there's no loading, transverse load, then the shear does not change. In the same way, we saw this relation for the moment and the shear, where the shear is actually the change of the moment with respect to x. So if there's if the moment changes from one point to another, then there's a shear. If there's a shear, it will change the moment. Got that? We saw this principle last lecture. With that said, we also looked at singularity functions. We defined how the singularity function gives us the ability to characterize something that has a singularity in the function. For example, it springs from nothing to something in a sudden manner. And the way we're identifying these is with these carets instead of regular parentheses kind of things. That identifies this as a singularity function where we have the x minus whatever the position is it starts at, and then to some exponent. Okay? This would be a 0 exponent springing from nothing to something. This would be a 1 exponent, which is a gradient, and a 2 exponent, which is a second order, and so on. Okay? A third exponent would mean it's going to look similar to this. It's just going to increase faster. We saw, so our basic relation when we're dealing with singularity functions is some function. Typically, it's going to be that loading function of x. We're going to have some coefficient. We're always going to have this x minus something, and it's going to be minus the x position moving from left to right of where that feature or that load starts. For example, in this one it was a, and this one it was a, and this was an a. So whatever it starts, that's the dimension. So if something starts, if we have a beam that's 20 inches long, it starts at 2 inches, that would be x minus 2. If it started at 5 inches, it would be x minus 5. And then some exponent, which actually tells us about what that loading function looks like. So we saw that when we have a singularity function, we have these, it's basically going from 0, basically this whole term is 0 if we have not yet gotten to the origin of that, and it's 1 if, which means it exists if we're past it. If we have 1, that's for a 0 exponent, going from 0 to 1. If we have any other exponent, it's just this becomes brackets, and this is just not considered if we haven't passed yet. We saw some specialized rules for integration and differentiation, basically, which means if we have an exponent of minus 2 or minus 1 or any negative exponent, but those are the two exponents we're going to be dealing with, then when we integrate, we're just going to ratchet that up one. So minus 2 goes to minus 1, and minus 1 goes to 0, and after that, we start integrating normally. We're often, when we're doing these, a lot of folks, a lot of books will go and change this x minus a to, say, the minus 2 power, or x minus a to the 2 power, a lot of times once we're in this form, they will show this as a x minus a squared. And that's okay once this exponent is greater than minus 1. But it's a little dangerous because it makes us forget that we're dealing with a singularity function. So you want to keep that in mind. We found last time that the key to analyzing slopes and deflections, and actually some of the more complicated shear and moment functions, is this table where we see how to characterize the loading function of a moment, of a force, of a distributed load, gradient, or exponent. Once again, we're always dealing, this is the loading function, which we're calling W of x. W of x for a moment has this form. This is defined as a positive moment, and it has an exponent of minus 2. If we have a point force, if it's located upward, that would be plus p. If it's downward, it'd be minus p. You got to be careful. This is different nomenclature than Beer and Johnson uses. The Beer and Johnson nomenclature will probably confuse you if you try to use it. This is the exponent for a force. This is the exponent for a distributed load. This is the exponent for a gradient. This is the exponent for a higher order function. This is the k that goes in here. This is the k that goes in here. All this is old news. We saw also that our shear is just, so our approach is we're going to write the equation for the loading, then we're going to integrate it to get the shear. We're going to integrate again to get the moment. Now, once again, we have this coefficient plus cm, but these, I told you, are going to be 0 for these first two integrations, so we can just ignore those. Keep in mind that those do spring into being, but if we applied our boundary conditions, they would go away. Now, once we get to the moment, when we integrate after that, we're going to do two things. First, we're going to, two additional changes. One is we're going to divide by the CA, and two, we're now going to have to do plus C theta, right? And we're going to retain that over CA, and then we're going to have a plus CY. And you also will have this plus C theta times X, right? Because that's going to integrate one time. Okay? This is all old news. This is how we handled basic slope and deflection calculations. Okay. With that said, we can recall also our constraints. If we see a pin, that's going to enforce zero displacement. So if we see a roller, that's going to also give a enforce displacement. If we have a fixity, that's going to give us both deflection and slope is 0. And if it's free, then it's no constraints. If it's a hinge, that will end up removing a moment at that point. Okay? We should be masters of this. With all this said, if we have a determinate beam, we're going to do it just like an indeterminate beam. We'll talk about that in a minute. So one more recollection is when we're analyzing for moments and slopes, for slopes and deflections, we can follow this little procedure from our handbook. We're going to use table 721. That's the table with the singularity functions for W of x. We're going to basically look at our beam, including reactions for everything we see on the beam, everything. This will have a term, and this will have a term, and this will have a term, and this will have a term. Anything we find on that beam, no matter what we find, every single loading will have at least one term in our loading function. If we have a function that is not shown in our handbook, like this one, we may need two terms. We need to approximate it with a down force distributed and an up distributed, and the summation of which becomes this, as it talks about in the handbook. So we write our singularity function for the entire loading from the left end to the right end, although we don't need any terms that appear at the full right end. We integrate once to get the shear. We integrate again to get the moment. We integrate again and divide by EI to get the slope, not forgetting our coefficient of integration. If we have any slope constraints, we'll impose those then. That makes it a little easier. Then we will integrate again to get the deflection, and we won't forget our coefficient of integration again. And then we will take any known displacements, plug them in, and solve for any unknowns. This is how we and then once we've gotten our coefficients of integration, c theta and cy, we then go and plug those back into our earlier equations where we didn't calculate those before to understand what any other terms of any other deflection, any other equations are. When we end up, we're going to have an equation for w of x, an equation for v of x, an equation for the moment of x, then an equation for the theta of x, and an equation for the deflection of x. All of these, for a correct answer, should then be simplified to the simplest form, just like simplifying fractions and such. Okay? That's how we do that. This is all old news that we learned last time. Now, when we analyze a beam, a statically indeterminate beam, we're going to do this exact same procedure. The only difference is not actually a difference. It just means it's a more rigorous, is we're going to have more unknowns. An indeterminate beam will have additional unknowns that will be solved by imposing our boundary conditions. We'll need to impose more and more boundary conditions. For example, if we have a beam that has two supports, that's going to be a determinate beam. If there's a third support, that's now indeterminate, but we can impose a deflection constraint there. If there's another constraint, that's another indeterminacy, but we can impose a constraint there. If we actually end up being fixed on the left end, that's even more constrained, but now we have a deflection and a slope constraint. So indeterminate beams are the exact same thing as determinate beams, except that we will just do more plugging and chugging when we implement the other constraints that made it indeterminate. It's as simple as that. Let's take a look at some examples and see how that works. Let's focus on a beam such as this one that has some constraint and some loading. And we can see on inspection that we have four unknowns. We have a horizontal reaction at A that we don't know, a vertical reaction at a moment at A, and a vertical reaction at B. This gives us four unknowns, and we really only have three equations to solve it from statics. The sum of forces in the x, y, and the sum of moments in the z. However, if we look at this, we see because NB is on a roller, when we sum our forces in the x direction, we're going to find that the reaction in the x direction at A is 0, which leaves us two equations to solve three unknowns. Since we don't have enough equations to solve from statics to solve this directly, we call this indeterminate. And we need to use something other than statics in order to completely solve it. So all we're going to do is, or fortunately, we could say that because for every reaction that's extra, we have that constraint introduces a known boundary condition, we're going to find that we can utilize that boundary condition to solve for any additional unknowns. This makes indeterminate beams just as easy to solve as determinate beams. So our upper figure here on this slide is the loading of the beam. Shows the loading of the beam. The lower one shows that our reactions at x equals 0. We know that our slope is 0 because of the wall, and our vertical deflection is 0, as is our horizontal deflection, which we already accounted for by inspection. We see at the right end that our vertical deflection is known to also be 0. And we're going to use those knowns to solve this beam. Now we can use successive summation of forces and moments to solve this, but the easiest way to solve these beams consistently is to write the singularity function for the loading and then integrate 4 times. We're going to integrate the loading function to get the shear, and note that the coefficient of integration is going to go to 0 if you solve for it. We're going to do that again for the moment. Once again, the coefficient of integration is going to go to 0. We then integrate again, dividing by EI, and find the slope. And we account for our coefficient of integration. And then we integrate again to get the deflection of the beam. And once again, we're going to get a coefficient of integration that pops up. We then are going to introduce our boundary conditions, plugging in that theta at x equals 0 is 0. And we're going to find that our coefficient of integration springing from the integration from moment to slope goes to 0. We'll introduce our boundary condition of the vertical deflection at 0, at A is 0. And that will tell us that what that other coefficient is. And then we're going to introduce or impose our boundary conditions at B, and we will finish solving for our last unknown. When we write our loading equation for this curve, we're going to find Wx equals R at A, the reaction at A. Now this is assuming that our reaction at A, we're assuming that that's in the positive direction. And we're assuming our moment acts in the positive direction. So we're assuming that our force at A acts in the positive direction, and that our moment acts in the positive direction. What that means is, we're then going to integrate back up. We're going to go back to the start of this slide. Consider for a moment the beam at right. So here we have a typical beam with a loading. We can see there are 4 unknown reactions. We have a vertical reaction at A, a force reaction. We have a vertical, a horizontal. Starting over again with this slide. Let's consider for a moment the beam at right. We can see we have a constraint, a wall constraint on the left end and a roller constraint on the right. We see this as a typical constant distributed loading. And if we look at this, we can see we have 4 unknown reactions. We're going to have a vertical unknown force at A and a vertical unknown force at B. We're going to have a horizontal unknown force at A and a moment in the Z direction at A. If we assume that all these reactions are positive, meaning that the forces all act upwards and that the moment acts such that it gives smiley face bending, which in this case will be like a positive Z moment, then we can actually notice that our reaction in the horizontal direction at A has got to be 0 since there's no loading in the x direction and no other constraints in the x direction. This is like applying the summation of force in the x direction to the beam. We then find that we have 3 reactions left to solve and 2 equations to solve them. The sum of forces in the y direction and the sum of the moments. This means we don't have enough equations from statics to determine all unknowns, which is why we call this indeterminate. Not because we can't determine it or a clever engineer can't solve this beam, but because statics alone will not provide enough equations to solve this beam. Fortunately, we're going to find that this is just as easy to solve as a determinant problem with just a little bit more algebra involved. We're going to find that the easiest way to solve this is writing singularity functions for loading, as we've said before. In fact, if we look at our beam again, we're going to then, having written the singularity function, we're going to impose the boundary conditions. Our boundary conditions, we see the left end. That wall imposes a no deflection in the horizontal or vertical directions, and it means that the slope at point A must be 0. Similarly, the deflection at B, the vertical deflection, must be 0. And we're going to utilize to solve this. We start by writing the singularity function. That's actually the easiest way to solve these kinds of problems because it gives us a single equation that covers all positions on the beam. If we wrote the loading function for this beam, we would pull out our singularity function table. We notice that since we assume that the reaction at A is acting in the positive direction, we find that's a positive magnitude RA. We write the singularity term, which means it starts at x equals 0, and forces have a coefficient or a exponent of -1. Since we assumed the moment at A was also acting in the positive direction, we find the sign of that term is positive. That moment also occurs at x equals 0, and moments get an exponent of -2. And then we find that the distributed loading, which is a constant loading, is acting in the negative direction, so we have a negative sign for that. That also starts at 0. It goes all the way to the end of the beam, so there's no adjustments needed, and distributed horizontal forces get a coefficient of 0. As we said last lecture, the terms at the right end of the beam do not need to be shown since we're always solving for some what the loading is between the left and right ends of the beam and not beyond the right end of the beam, which means that that term will always be ignored, and therefore we can just keep not write it at all. We now, having the loading equation, we will integrate that mother twice, once to get the shear and once to get the moment. Each time we will get a coefficient of integration, which if we imposed our boundary conditions like a shear at some value and a moment at some value, we would find that that coefficient is 0. Therefore, we often will ignore the constants of integration for those first two integrations. We then divide the moment equation by EI and integrate twice more, once to get the slope and once to get the deflection. This time we must include the constants of integration. Once we have that, we insert each boundary condition successively, the slope boundary conditions and the deflection boundary conditions. And each time we do that, we can solve for different unknowns. Sometimes that, or often that unknown can be determined directly. Sometimes it will have to be carried forward and additional algebra will need to be solved to determine those unknowns. This is fairly straightforward and is not any different than how we solved determinate beams. So let's take an example at how this is done, and we'll move to the next slide. Let's take Beer and Johnson sample problem 9.3. A quick glance shows that this is also an indeterminate beam, and what we're going to try to do here is determine the equation of the elastic curve and the slope at A. We actually have at least two methods to solve this. One is just using statics, where we're going to make a section cut. In this case, we only need to make one section cut, and then summation of forces and moments to write the equation. We're going to show you how that is solved on the next set of slides. And then the alternate method is to write the singularity function of the loading and then perform successive integrations and insertions of boundary conditions. This is actually the easiest way to solve this problem. So let's look at method 1. If we used method 1, we would make a section cut anywhere between A and B. We would put all the loading and the reactions on the left end of that beam on the diagram as shown. We would see that the line of action of that gradient loading is going to occur 1/3 from the right end of the beam. So if we're making a section cut X inches from the left end, then that will be at 2/3 X is where that resultant force is located, and the magnitude of that, first we have to figure out the magnitude of the right end. If that loading is W at the right end of the beam, then the magnitude of the loading right at the point where we made our section cut, point D, will be W times X over L, because it's going to be proportional since it's linearly increasing. We then note that the total force on that segment of beam is that W, which is WX over L. It's going to be 1/2 of that since it's the area under this curve and we have a gradient. And we see that it's located at 1/3 of the way from the right end of the beam, so it's 1/3 x. We are also going to assume that our shear on the beam is positive using beam notation, so chopping off the beam as we move from left to right is positive, as shown in our moment is positive if it creates smiley face bending. We then sum our moments. This is summing the moments, and this is assuming that a negative z direction or a clockwise moment is positive. If that's true, then RA times x minus 1/2 WX over L, right? Times, so we remember our function is WOX over L, and it's multiplied by x over 2. That's why it's WX squared over L. It's located x over 3. And then we have the moment term on the right end, which is now in the negative direction of what we assumed. That's got to be equal to 0. We then can apply algebra to solve that for the moment, and that's our function for m of x. We now can integrate that twice, recalling that the second derivative of the deflection times EI is equal to the moment, and then we can integrate that. First to get the slope, as shown on the first line, and then again to get the deflection each time we see a coefficient of integration springing into being. We then can apply our boundary conditions. For example, the deflection, the vertical deflection at A is 0, and at L is 0, and the slope at L is 0. And from our first boundary condition, we find out C2 is 0. From our second two, we can solve for the other unknowns, which is C1 and the reaction at A. That's done here by combining those equations, and we find that RA is equal to that value acting in a positive direction. So we see that the equation for the elastic curve, if we plug those unknowns back into this elastic curve that we had before, we can write the elastic curve. This is shown as y, but it's really y of x because it's a function of x. And if we then take the derivative of that, or just recall that our slope is already the derivative, we can find out, set this equal to 0 and calculate where the slope is maximum, a local maximum or minimum. We find out that that's a maximum or minimum at x equals 0, and we then plug in that value to calculate the slope at A. So that is method 1. Method 2 is to calculate this by hand. I'm going to stop and back up. No, I'm going to keep going. So method 2, this is a typo. This is actually method 2. And what we're going to do at first is write our singularity function for the loading. We see that the reaction at A, if we assume that's positive, is going to be positive. It starts at x equals 0, and it has a coefficient of -1. We see that this kind of gradient loading, what we're going to put in first is the k, and since this is acting downward, it's a negative. The slope of this loading is actually going to be WO divided by L, so we're going to put that in as our k. It starts at x equals 0, and coefficients for this kind of gradient loading are 1. We integrate that once, and we find that since the first term has a -1, all the integration or syntegration does is cause that to go to 0. For the next term, since we had a coefficient of 1, that now goes to 2, and that throws a 2 in the denominator, and we have a coefficient of integration. If we plug in our shear at 0, just positive side of 0, we know that must be RA. So plugging in x equals 0 into our equation, we find out that CV must be 0. Therefore, the shear of x as a function of x is just RA, x minus 0 in brackets, to the 0 power minus W over 2L, x minus 0 squared. We integrate that puppy to find the moment, and we find our 0 coefficient goes to 1, our 2 coefficient goes to 3 and throws a 3 into the denominator. We also get a coefficient of integration, which I'm calling the coefficient from the moment integration. If we plug in our boundary condition that the moment, the external moment at 0 is 0, we find out that Cm is also 0, which gives us our moment equation for the beam as shown at right. We then integrate that again, this time dividing by EI, and we get the next term. We now have a 1 over EI term. We put everything else in brackets. We see the 1 coefficient goes to 2 and drops a 2 into the denominator. The 3 coefficient goes to 4 and drops a 4 into the denominator. And we have a coefficient of integration, which we're calling C theta. We then can plug in our boundary condition that the slope at L must be 0, since the beam is in a wall. And we find out that C theta, if we do a little algebra on that, is equal to the term shown over at the right, WOL cubed over 24 minus RA L squared over 2. Plugging that back into our equation for theta, we get what's shown next. We now integrate that to get the deflection. Our coefficient of 3 on the first term, or of 2, goes to 3, throws a 3 into the denominator. Our second term coefficient of 4 goes to an exponent of 5 and throws a 5 into the denominator. And then we have the next two terms, which just get multiplied by x, and a coefficient of integration, cy. If we plug in our boundary condition that the deflection at 0 is 0, we find that cy is 0. If we plug in our last constraint that the deflection at y is 0, we can now solve for the reaction at A, which is done in that last line. And we find that the reaction at A is in the positive direction, WL over 10. Now, we can rewrite our equation of the beam, our loading by plugging in the unknowns, our shear, our slope, and our deflection, and solve for any other terms we want. So, that is how we solve indeterminate beams, using the exact same procedures we did for determinate beams, except now we're imposing additional boundary conditions. Enjoy.